So for my final project, I am looking at modeling volcanic eruptions with Bayesian methods. I start with an overview of a particular paper, which implements Bayesian hierarchical modeling, and also complete some applications of my own. So some background on volcanic eruptions. They are, of course, a natural hazard with significant impacts on environment, climate, and society. They are considered unpredictable in the field of volcanology, and it's still a great area of study, trying to understand the precursors to severe eruptions in an effort to predict them. Here, statistical models can aid in this prediction. So the explosivity of a volcano is measured with a logarithmic scale called the VEI. Some examples include Mount Vesuvius and from Pompeii, which was a VEI of 5, and the 1980 Mount St. Helens eruption was also a VEI of 5. The VEI is determined by factors such as the volume of erupted material, height of the eruptive plume, and the duration of the eruption. So for hazard modeling, we can think of our data as being a renewal process. This is a stochastic process that can model the occurrence of events over time, where we find the time between consecutive events, called the inter-arrival time, and assume that they are independent and identically distributed for some distribution. After each event, the system renews and resets for the next event. The hazard rate refers to the instantaneous probability that an event will occur at a given time t. So an example, each time a light bulb burns out is replaced with a new one, and the process of a renewal starts again, where the lifetime of each bulb is considered a random variable with the same distribution, making the time between replacements independent and identically distributed. In this example, the hazard rate would describe the instantaneous failure rate of a light bulb at a given time, assuming that the light bulb has survived up to that time. I will be focusing on both the gamma and the Weibull distribution for renewal processes. In a gamma distribution, a higher shape alpha parameter indicates a more peaked distribution, so the inter-arrival times clustering around their mean, and a larger scale beta is going to result in proportionally larger average time between events. While in a Weibull distribution, a higher shape parameter indicates an increasing failure rate over time, so for alpha greater than 1, later events are more likely, so increasing hazard as time goes on. And the opposite is true for alpha less than 1. Then beta determines when the majority of events occur relative to the hazard rate. You can see some of the differences in the plot as well. With higher scale values, gamma has a larger tail than Weibull. And for both Weibull and gamma, when the scale parameter is 1, this is the same as an exponential distribution. Weibull is often used in volcanic literature because of its interpretation of parameters with time to failure models. So one issue with volcanic prediction is that there is very limited reliable data per volcano to create prediction models based off of, specifically because most experts advise only modeling for VEI 3 and above, because eruptions less than that are also less hazardous, but they're also less reliable for statistical prediction because the geological record is biased to recording larger eruptions. So there might be eruptions that are happening less than VEI 3 that we don't know about, so it's harder to base statistical models off of these. This paper, called Forecasting Eruptions at Poorly Known Volcanoes Using Analogs and Multivariate Renewal Processes, attempts to address this issue. So, out of 23 empirical analogs, that is, volcanoes that are geologically similar, they identified a subset of 17 volcanoes with compatible statistical features and produced a forecast for VEI 3+ events. So the main objective is using other volcanoes to allow for a better prediction on ones where there is limited historical data. So different volcanoes are going to have different periods and clustering patterns. So in order to use other volcanoes to predict at a new one, they have to account for this variation. So they explore 3 different models listed here based off of this initial Weibull hazard rate function. So M1 allows for some variation in the activity level between volcanoes. So if Yi does not have statistically different distributions for different I, which are different volcanoes, then the set of volcanoes are considered as being good analogs in terms of activity levels. Similarly, the second model, M2, allows for variation in clustering behavior with the random variable Zi, and so statistically insignificant difference in the Zi's distribution will indicate that the various individual volcanoes share similar shapes and thus can be considered good analogs in terms of clustering behavior. And then the third model is using both these random variables, Yi and Zi, to distinguish both differences in activity level and clustering behavior between volcanoes. These models produce Weibull hazard rate functions, but the shapes of the hazard rate functions depend on the combinations of z, y, and the parameters alpha and beta. Using analog volcanoes can produce more robust estimates of alpha and beta in the intensity in the Weibull hazard rate function. The statistical model effectively maps these volcanoes onto each other for forecasting purposes through a time rescaling. So getting into the specific model structure, they use 3 chains, half normal priors for alpha and beta, and then yi and zi have gamma priors, where sigma y and sigma z have weakly informative half-t prior distributions. So zi is going to be capturing the hidden factors influencing the shape parameter, and yi captures the hidden factors influencing the rate parameter. So they use an MC algorithm, which generates the samples from the joint posterior distribution of alpha, beta, yi, zi, sigma y, and sigma z, given the in-arrival times for I equals 1 through m volcanoes. And they use the JAG software. So this paper was focusing on predicting on the Tongariro volcano in New Zealand, which I showed in that first slide. And this has very limited historical data, and so the potential analog volcanoes were selected to satisfy based off of 2 of these 3 constraints. So one needs to be a composite volcano, which are the classic large cone-shaped volcanoes built up from layers from previous eruptions. 2, it needs to be erupting basaltic to andesite compositions, which is referring to the amount of silica present in the magma, which plays a major role in volcanic activity. And then 3, it needs to be located on a convergent margin, which has to do with the tectonic setting of the volcano. So they ended up with 23 of these analog volcanoes, and 17 were determined to be statistically analogs. So they found if it was a statistical analog by calculating the proportion that the MCMZ samples of the posterior distribution of Zi or Yi overlap with the Tongariro values of Y and Z. So for each volcano I, if the proportion for the shape parameter in the model is greater than 0.2, then the ith volcano is a good analog. This ended up highlighting how statistical analogs were better forecasting than empirical. So the inter-arrival times for VEI greater or equal to 3 eruptions were simulated for Tongariro and the 17 statistical analog volcanoes. Simulations were drawn from the Weibull distribution, parameterized using the posterior means obtained from the model M3. So model M3, which was the one allowing variation in both activity level and clustering between analog volcanoes, was found to be the best based off of residual analysis. So the parameters for this Weibull distribution are defined as seen in this equation, where mu zi and mu yi, mu alpha, and mu beta are the mean of the posterior distribution. So the posterior distribution of model M3 suggests that there is a 5% probability that an eruption of VEI greater than or equal to 3 will occur at Tongariro in the next 50 years, and a 50% probability before the year 2967. So these forecasts from model M3 using analog volcanoes produced much narrower, credible intervals than that from the Weibull renewal processes using only Tongariro. This is highlighting the usefulness of this analog approach. Additionally, the posterior mean for alpha was found to be 0.75, and the mean for beta was 0.332. So I explored a few different approaches myself, taking inspiration from this paper, and I will be touching on the non-hierarchical model first, in which I attempt to model all of the recent eruptions for Tongariro without specifying particular VEI. And then I extended this model to incorporate these other random variables as the paper did in order to utilize the statistical analog volcanoes as a means of improving forecasting for Tongariro. In doing this, I also followed the standard procedure of only considering eruptions with VEI 3 or greater. So these are the histograms of the inter-arrival years for Tongariro and 3 empirical analogs based on the record of the past 12,000 years with a VEI 3 or greater. So we can quickly see that Popocatépetl looks quite different, which is reassuring because it is actually one of the volcanoes from the empirical list in the paper that was not deemed a statistical analog. I ran models using just Calbuco and Avachinsky, as well as Popocatépetl, particularly to see how the different Zi values and Yi values were. Also worth noting the sparsity of Tongariro, which is highlighting one of the reasons for the study in the first place, which is trying to predict on volcanoes with very limited historical data. So for this model, I took all the VEI levels and eruption dates in the past 12,000 years for Tongariro, which was a total of 76 instead of just 6, as seen in the previous histogram. And then we assume the interarrival times are independent, follow a gamma distribution, and parameters alpha and beta, I use log normal priors for these so they have positive values. So recalling alpha controls the distribution skewness and beta is controlling the spread. And here it is the number of groups, which are the volcanoes, which depending on if I included all three, it is just 2 to 3. I also tried the same model where we just used the Weibull distribution as the likelihood instead. So with this model using a gamma likelihood, I got posterior parameter estimates for alpha as 1.43 and beta as 0.643. And we end up with a mean interarrival time of 2.2 years. And recall this includes both VEI 1 and 2, which are not very severe and a lot more frequent. So this is a reasonable time. What kept happening with the Weibull likelihood is getting really skewed predictions that are much lower than the mean, the observed mean. I did run into some issues with convergence, and even when I increased the thin values, number of chains, more samples, larger burn-in, I would be waiting for 30 minutes for it to run, which really I know is not that long, but it was hard to justify when I was trying all these different things with this time frame of this project. So I also attempted to replicate a similar method as in the paper. So here we stick to modeling the volcanoes with VEI 3 or greater, and using that list of 3 that I mentioned before, we model the interarrival times for each different volcano by its shape and rate, in which alpha and beta have weakly informative truncated normal priors, and Zi and Yi have gamma priors with the half-T distribution hyperpriors for sigma Y and sigma Z. And this approach scales the differences in periodicity and clustering based on the volcano in the hierarchical model. This table is showing the posterior means in credible intervals as the result of this model. And some interesting things to note here is that for Popocatépetl, which is group 3, is worth noting how much higher its Z value is, which is in line with the very different density of the interarrival times and being deemed not a statistical analog in the paper as well. So Z is the one that's controlling the clustering, so it's saying that this volcano has a very different value of clustering than Tongariro, and it is probably not good statistical analog. So these are the plots using a gamma likelihood, as mentioned before. The posterior predictive distribution very nicely contains the mean interarrival time of about 400 years. And in figure 8, this is showing the full simulated density based off of how one calculates the alpha and beta, as in line with the paper, compared to the observed density of our data. So similar to what happened with the non-hierarchical model, when I used a Weibull distribution instead of a gamma as the likelihood for the interarrival times, I would get a very skewed predictive distribution that tend to underpredict based off compared to the observed mean. I do not know exactly why this was the case, beyond something in the data, something in my code, or something with convergence, or some combination. I did have some issues with the convergence, like I mentioned before, so that definitely could be part of it. It was based on the plots. It seemed that the Weibull, for whatever reason, like I was mentioning, was failing to capture the tail behavior and was ignoring the longer interarrival times, and whereas the gamma was able to spread out its distribution a little more. So, sort of back to the paper and summarizing that as well. The paper found that they could improve the hazard forecast at single volcanoes with poor or incomplete eruptions by applying a multivariate Weibull renewal process that borrows strength from the analog volcanoes. These volcanic systems have similar geologic and tectonic and statistical features to the target volcano, but longer or more complete eruption records. And so using Bayesian inference, they can determine which volcanoes in a set of candidate volcanoes can be considered good analogs in terms of eruption occurrence. And then summarizing, like I've mentioned before, in my replication, despite the Weibull model used more frequently in volcanic prediction literature, when I used the gamma as likelihood, I got better results. Also worth noting that another limitation could be that I only did use 3 volcanoes, and out of those 3, only 2 were actually statistical analogs. And in the paper, they actually ended up doing something similar, where they used the two most statistically analoged volcanoes based off of the Z and the Y's to Tongariro, and still got very wide credible intervals compared to when they used all 17 for forecasting. And so that could be another issue that with my applications. Overall, I thought this was a super cool application of Bayesian inference and hierarchical modeling used in volcanic predictions, and it was really cool to try to explore in my applications, and I wish I had more time.